Strong acid dissociations are not treated as equilibria. Rather, we think of them as reactions that go to completion, that is, as irreversible reactions. The equations shown here are those of the strong hydrohalic acids and oxoacids. Notice that the single arrow is used in each case. Acids can be classified according to the number of protons they are able to donate. A monoprotic acid has 1 proton to donate. The prefix mono means 1. For every 1 mole of a monoprotic acid, 1 mole or 1 equivalent of hydrogen ions or hydronium ions is produced. Hydrochloric acid is an example of a monoprotic acid. A polyprotic acid has more than 1 acidic hydrogen atom. Sulfuric acid, H2SO4, is a diprotic acid as it has 2 acidic hydrogen atoms. The prefix di means 2. For every 1 mole of a diprotic acid, 2 moles or 2 equivalents of hydrogen ions or hydronium ions are produced. Polyprotic acids lose protons in a stepwise fashion. Let's consider sulfuric acid as an example. For sulfuric acid, the first ionization is that of a strong acid. Sulfuric acid in water ionizes to give hydrogen ion and hydrogen sulfate ion. Notice the use of a single arrow to denote the irreversibility of the first ionization of sulfuric acid. The first hydrogen leaves sulfuric acid readily for reasons similar to the ones mentioned for chloric acid. Like chlorine in chloric acid, sulfur in sulfuric acid also has a high oxidation number and increased electronegativity. It too causes the HO bond to become more polar and hastens the departure of H+. Additionally, sulfuric acid's conjugate base, hydrogen sulfate ion, is stable as it enjoys charge delocalization. The negative charge in the ion is spread over 3 oxygen atoms in the resonance hybrid of the ion. This decrease in the magnitude of the negative charge at each oxygen atom stabilizes the ion. The second ionization, that is, the ionization of hydrogen sulfate ion, occurs only to a small extent. Thus, the hydrogen sulfate ion is considered a weak acid. Notice the use of a double arrow to denote this reversible reaction. Hydrogen sulfate ion is weakly acidic since it is not so easy to get a negatively charged species like hydrogen sulfate ion to lose H+. After doing so, it becomes the sulfate ion SO4 2-, which has a double negative charge. Species are not fond of bearing single negative charges. They are even less fond of bearing negative charges of greater magnitudes. Having said that, though it is classified as a weak acid, hydrogen sulfate ion is not that weakly acidic. Among the weakly acidic species, some are stronger than others, as is the case for hydrogen sulfate ion. It is because the double negative charge is delocalized over 4 oxygen atoms in the resonance hybrid of its conjugate base, sulfate anion. Here are some examples. Calculate the pH of an aqueous solution at 25 degrees Celsius, that is, part A, 0.035 molar in hydroiodic acid, part B, 1.2 times 10 to the power of negative 4 molar in nitric acid, and part C, 6.7 times 10 to the power of negative 5 molar in perchloric acid. Hydroiodic acid, nitric acid, and perchloric acid are all strong acids, meaning that they are 100% ionized. So the concentration of hydronium ions in each solution is the same as the stated concentration of the acid. Therefore, use pH equals negative log of hydronium ion concentration to calculate pH. Thus we get for part A 1.46, for part B 3.92, and for part C 4.17. Here are more examples. Calculate the concentration of HCl in a solution at 25 degrees Celsius that has pH of 4.95, 3.45, and 2.78 in parts A, B, and C respectively. This time around, we are given pH and are asked for HCl concentration. So we use the hydronium ion concentration formula, which is equal to 10 to the power of negative pH, to convert pH to hydronium ion concentration. In a strong acid solution such as HCl, the hydronium ion concentration is equal to the acid concentration. Thus, we get 1.1 times 10 to the power of negative 5 molar, 3.5 times 10 to the power of negative 4 molar, and 1.7 times 10 to the power of negative 3 molar for parts A, B, and C respectively. As pH decreases, acid concentration increases. This list shows equations of the dissociation in water of strong bases, namely the hydroxides of alkali metals and the heaviest alkaline earth metals. Note the use of the single arrow to denote the irreversible reactions. Just as acids can be classified according to the number of acidic hydrogens they have, bases can be classified according to the number of hydroxide ions they produce in water. Monobasic bases are bases that produce only 1 mole of hydroxide ions per mole of base. The prefix mono means 1. For every 1 mole of a monobasic base, 1 mole or 1 equivalent of hydroxide ions is produced. Sodium hydroxide is an example. Some strong bases, such as barium hydroxide, produce more than 1 mole of hydroxide ions per mole of base. It is an example of a dibasic base. The prefix di means 2. For every 1 mole of a dibasic base, 2 moles or 2 equivalents of hydroxide ions are produced. Here are some examples. Calculate the pOH of the following aqueous solutions at 25 degrees Celsius. Part A, 0.013 molar of lithium hydroxide, and Part B, 0.013 molar of barium hydroxide. Lithium hydroxide and barium hydroxide are strong bases, so we use reaction stoichiometry to determine the hydroxide ion concentration. Then we use pOH equals negative log of hydroxide ion concentration to determine pOH. Part A. The hydroxide ion concentration is simply equal to the concentration of the base. Therefore, hydroxide ion concentration is equal to lithium hydroxide concentration, which is equal to 0.013 molar. pOH is therefore 1.89. Part B. The hydroxide ion concentration is twice that of the base, since 1 mole of barium hydroxide gives 2 moles of hydroxide. Therefore, hydroxide ion concentration is equal to 2 times barium hydroxide concentration, which is equal to 2 times 0.013 molar, which is equal to 0.026 molar. pOH is therefore 1.59. Note that while the solutions in parts A and B have the same base concentration, they do not have the same hydroxide concentration. Therefore, they do not have the same pOH.